Hello students. As you know, nucleophilic substitution reaction occurs when the substrate, here it may be aliphatic or aromatic, is attacked by a nucleophile with the removal of a leaving group. So in this lesson, we shall be focusing on aromatic nucleophilic substitution reactions. In content, we'll cover introduction, types of mechanism, that is, different types of mechanism involves in aromatic nucleophilic substitution reaction, and the factors which affecting the rate of aromatic nucleophilic substitution. Introduction. As you know, replacement of hydrogen or substituent on an aromatic ring by nucleophile is known as aromatic nucleophilic substitution reaction. Unlike aliphatic compounds, nucleophilic substitutions on aromatic rings are relatively less common. The reasons for unusual reactivity of aromatic rings towards nucleophilic substitution is: Number 1. The presence of aromatic ring pi electrons make the aromatic system an electron-rich, which are more likely to be attacked by electrophile rather than nucleophile. If nucleophile attack the aromatic ring, then there is a partial double bond character between the carbon of the ring and the halogen atom. As result of delocalization, this lone pair of electron move through conjugation with the pi electrons of the aromatic ring. So, the halogen atom becomes firmly bonded to the aromatic ring and cannot be replaced easily. The second reason is that, during resonance, the aromatic ring loses its stabilization by attack of nucleophile. Therefore, under drastic conditions, that is, under high temperature or high pressure, in the presence or absence of catalyst, aromatic nucleophilic substitution may take place. On the other hand, properly substituted aromatic compounds, having -R, or -I group, at ortho, or para position, undergone nucleophilic substitution, with less difficulty, because -R and -I groups are activating groups for aromatic nucleophilic substitution. These group decrease electron density on the aromatic ring and activate it for nucleophilic substitution. This low reactivity can be changed dramatically by changes in the reaction conditions. When the aryl halide is activated by substitution with strongly electron-attracting groups, and when very strongly basic nucleophilic reagents are used. Therefore, under special substrate structure, nucleophile properties, and reaction conditions, aromatic substitution reactions are facilitated. Types of mechanism. When we talk about mechanism, which are successful at aromatic substrate, are mainly of four kind. Number 1, the reaction in which nitrogen of diazonium salt is replaced by nucleophile, that is Arsn1 mechanism. Number 2, reaction activated by electron withdrawing group at ortho and para position, with respect to leaving group, that is addition-elimination mechanism. Number 3, reaction are catalyzed by very strong base, and proceed through arine intermediate, that is benzene mechanism. And the last one is reaction are initiated by electron donor, that is SRN1 mechanism, which involve radicals. Now we will discuss one by one all type of mechanism. Come to ARSN1 mechanism, that is aromatic nucleophilic substitution unimolecular reaction. As we know, the SN1 mechanism represent first-order nucleophilic substitution reactions, where the rate of reaction depends only upon the nature of substrate, and there is no effect of concentration of incoming nucleophile. Such substrates are rare to find, unless highly substituted benzene rings are present, or with diazonium salts. This mechanism operates by the reaction of diazonium salts with nucleophiles. When primary aromatic amines are treated with nitrous acid, that is HNO2, under cold conditions, they give diazonium salts. These diazonium salts are good substrates for reactions proceeding via SN1 mechanisms. This is because, in diazonium salts, the leaving group is dinitrogen, which is an excellent leaving group, and on leaving, it affords a positive charge on benzene ring, making it available for attack by incoming nucleophiles. The aryl cation is highly unstable, but the driving force resides in the strength of the bonding in the nitrogen molecule, makes it a particularly good leaving group. Now we'll see the mechanism. The mechanism of ARSN1 involves two steps. Step 1 involves the formation of the carbocation. See the reaction. When diazonium salt lose N2 molecule, then it will form carbocation, which is a intermediate. Step 1 is slow step, hence rate determining step. Come to step 2, it involves the attack of the nucleophile, that is Y-, on the benzene ring, to form a substituted product. Next mechanism is addition-elimination mechanism. The SNAR mechanisms follow addition-elimination steps, where, first the incoming nucleophile gets attached to the substrate, and then elimination of leaving group takes place. In this type of reactions, aryl halides react with strong nucleophiles to give substitution products. As mentioned before, for such mechanisms, suitable electron withdrawing groups on the substrate favors the reaction, as they stabilize the intermediate carbanion. Intermediates of this type are stable salts, called Meisenheimer or Meisenheimer-Jackson salts. Nucleophilic aromatic substitution occurs with a variety of strong nucleophiles, including O- or minus, NH2-, SR-, NH3, and RNH2. For these reactions, the reactivity of nucleophiles is significantly enhanced if the reaction is carried out in polar aprotic solvents. In polar aprotic solvents, the incoming nucleophile anion becomes soluble, though it may not get stabilized by hydrogen bonds. Further, the position of substituent that best facilitate the reaction is ortho or para substitution. This is because only the negative charge acquired by the ring may get accommodated by the substituent. In contrast, if the substituent is present on the meta position, no stabilization is achieved. This becomes clear from the resonating structures. Increasing the number of electron withdrawing groups also increase the reactivity of the aryl halides towards nucleophilic substitutions. This mechanism involves two-step. Step 1 involves addition of the nucleophile. In this step, the incoming nucleophile attacks at the same position where the leaving group is attached, Such attack is called ipso attack, to form a resonance-stabilized carbanion. This step is slow step, hence rate-determining step. And step 2 involves the elimination of the leaving group. In this step, there is loss of leaving group, leading to the formation of aromatic ring. Step 2 is fast step, because the aromaticity of the benzene ring is restored. The SNAR reactions follow a second-order kinetics, because rate of reaction is directly proportional to both aryl halide and nucleophile. Third mechanism is elimination addition mechanism. Without a substituent, it is very hard for aryl halides to undergo nucleophilic substitution, and only under drastic conditions they react with nucleophiles. Such reactions indicate that nucleophilic aromatic substitution, by an elimination addition mechanism, lead to products with substitution on the carbon, which is directly bonded to the leaving group, or to the carbon adjacent to it. Unactivated aryl halide, having at least one hydrogen atom in ortho position, undergo aromatic nucleophilic substitution in presence of very strong base, like KNH2 or NaNH2, in liquid ammonia. The incoming group does not always take the position vacated by the leaving group. This is called sine substitution. Consider the reaction of chlorobenzene with sodomide in liquid ammonia. Star mark in chlorobenzene indicate the position of leaving group. When it undergo elimination reaction, followed by addition reaction, there is chance of getting two different product. The mechanism involves elimination followed by addition, hence it is called elimination addition mechanism. These elimination addition reactions proceed via benzene intermediates. Therefore, it is also called benzene mechanism. Mechanisms of nucleophilic aromatic substitution involves two-step. Step 1 is the elimination of hydrogen and halogen. Here, nucleophile, that is, amide ion, removes the ortho hydrogen, with subsequent loss of the chlorine, which is a leaving group, to generate benzene intermediate. The benzene intermediate has a triple bond in benzene ring. The triple bond in benzene is unusual, as each carbon of the 6-member ring is sp2 hybridized, having one sigma bond and 2 pi bonds. Step 2 is the addition of nucleophile, that is NH2-, to benzene intermediate, to form carbanion, which undergo protonation by solvent like liquid NH3, and this benzene intermediate is attacked by NH3 at either of two positions to give different product. SRN1 mechanism. SRN1 stand for substitution radical nucleophilic unimolecular reaction. This reaction type was discovered in 1970 by Bonnet and Kim. Due to involvement of radical anions, the SRN1 reactions may occur via a chain mechanism. This mechanism is initiated by single electron transfer from a chemical catalyst, or from an external electron source, to the substrate, which produces a radical anion. In this SRN1 mechanism, the initial attack takes place via an electron donor, rather than a nucleophile. The radical anion thus formed leads to removal of leaving group, and left behind a radical, available for attack by the incoming nucleophile. Interestingly, involvement of radicals allows a chain mechanism for SRN1 reactions. A chain mechanism is a self-sustaining reaction, where the reaction continues by the formation of reactive intermediates that recycle. During product formation, these intermediates then react to continue additional processes, keeping the continuity of reaction. It involves substitution on an aromatic compound, mediated through a nucleophile, and an intermediary free radical species. The reaction is usually performed either in liquid ammonia, or dipolar aprotic solvents, such as dimethyl sulfoxide, or hexamethyl phosphoric acid. Being a chain reaction, the mechanism follows an initiation, propagation, and the termination steps. As shown in figure, the aryl halide, which is a substrate, first accepts an electron from a donor, and becomes an anion radical, which loses the halide anion, giving rise to an aryl radical, which can be easily attacked by the nucleophile to form a new radical anion, which subsequently leads to the product formation. During the chain propagation step, the aryl radical, with attached nucleophile, get recycled to give intermediate radical through intermediate. Factors affecting rate of aromatic nucleophilic substitution reaction. The common factors, which influencing the rate of all the four types of mechanisms, are: Number 1. Effect of substrate structure. 2. Effect of leaving group. And last one is effect of attacking nucleophile. We shall discuss each of them separately. First factor is the effect of substrate structure on the rate of nucleophilic aromatic substitution reaction. In SNAR mechanism, if the electron withdrawing groups are present on the ortho or para positions to the leaving group, great accelerations in rate of reactions have been observed. On the contrary, if the substrate has electron-donating substituents, then reactions go slower. For common substituents, following is the order of increasing ability to activate aromatic rings for SNAR substitutions. As can be seen, the nitrogen-containing substituents act as good ligands, enhancing the rate of reactions, and the position of substituents also greatly influence the rate of reaction. For example, if the electron withdrawing group is present at meta position, then no delocalization of charge takes place, and reactions become difficult. As you know, electron withdrawing groups increase the rate of reaction. From this, it follows that, if more electron withdrawing groups are there, faster is the reaction, because electron withdrawing groups stabilize the intermediate carbanion. See the diagram. Trinitrochlorobenzene is more reactive than dinitrochlorobenzene, which is more reactive than 4-nitrochlorobenzene. In benzene mechanism, two factors affect the position of incoming group. First factor is that, if meta-substituents are present, then two benzenes may be formed, based on which protons are more acidic. More acidic protons will be removed, form benzene formation. An electron withdrawing Z group favors removal of the ortho hydrogen, whereas an electron releasing Z group favors removal of the para hydrogen. The second factor is that the arene once formed can be attacked at two position. The favored position for nucleophilic attack is the one which leads to more stable carbocation intermediate, and also depend on field effect of Z. For substituents with -I effect, the more stable carb anion is the one in which the negative charge is closer to the substituent. Effect of leaving group. Leaving groups, like halide, sulfate, sulfonate, Nr3+ are good leaving group in aliphatic nucleophilic substitution, which are also common leaving groups in aromatic nucleophilic substitutions. But the groups like NO2, OR, OAR, SO2R, and SR, which are generally lost in aliphatic systems, are good leaving groups when attached to aromatic rings. Stable anions are good leaving groups, which results in lowering the activation energy, while reaction rate is increased. An approximate order of leaving groupability is given below. Amongst the halogens, fluoro is generally a much better leaving group than the other halogens, because of its highest electronegativity. The order is usually fluoro is more reactive than Cl, which is reactive than Br, which is reactive than I, but not always. Fluoro and nitro are good leaving groups when SNAR mechanism is operating, but in benzene mechanism, fluoro is the poorest leaving group. Last factors which affect the rate of reaction is effect of attacking nucleophile. It is not possible to construct an invariant nucleophilicity order, since different substrates and different conditions lead to different orders of nucleophilicity. However, an overall approximate order is given below. In case of aliphatic nucleophilic substitution, nucleophilicity is generally dependent on base strength, and nucleophilicity increases as the attacking atom moves down a column in the periodic table. However, there are many surprising exceptions to these facts. O-, a stronger base than Aro-, which is a poorer nucleophile. The cyanide ion is not a nucleophile for aromatic systems, except for sulfonic acid salts, and in the von Richter and Rosemond von Braun reactions, which are special cases. But it is an excellent nucleophile for aliphatic system. Thank you.